Stop worrying about homework and start learning with confidence. This is Ask Learn. Complete help for every subject. Like, share, subscribe for daily learning videos.
Okay, so this problem we have here is a little tricky. It's going to involve some of our knowledge of gravitational forces, so we're going to have to dig some of that back up. But I have a little diagram of the situation here. So on the left side here, we have this rod hanging vertically straight up and down from the ceiling. And on the right over here, I have it as it's been swung up at an angle phi from the vertical line here. This dotted line just represents straight up and down. So in both cases, we have a magnetic field that is also straight up and down. So in this case, we have a current flowing from back to front here of this rod. This rod is supposed to be three-dimensional here. This front end here is closer to you than the back end here. That's what this shorter string represents. So this is supposed to be going into the page three-dimensionally, and then you have magnetic field going up and down, so it would be perpendicular, the magnetic field to the flowing current, and we have current flowing from back to front. So once a current is applied to it, the magnetic field causes it to swing up at an angle phi. So before we start working on any numbers, let's just write a force diagram for this, because we know we're going to have two forces acting on it. Because it's hanging, it has a force of gravity, which I will call F sub g, and because there is a current in a magnetic field, we have a magnetic force, which I will call F sub b, just to keep the two forces separate while we're working. So our knowledge of gravity tells us that F sub g is equal to G, which is 9.8. I'll just write that up here. This is a common constant that comes up all the time, so having this memorized doesn't hurt in any way whatsoever. G G is equal to 9.8 meters per second in SI units. You can also do it in feet per second, but we're going to stay in SI units here. So gravity is 9. I'm just going to call it G from here on out. We know the force due to gravity is equal to G times our mass. And mass is in kilograms. And we are given the mass of this rod, so this is something that we can calculate. Just simply multiply the mass of the rod by G, which is 9.8. That will give you this F sub G. So we have that. Now we need direction, because this is a three-dimensional problem, and we do need to know direction to keep all of our forces straight and to be able to find our final answer here. So gravity always, no matter where this is at, gravity is always pulling straight down. Gravity is one of the easiest forces to deal with. Always points straight down from the center of mass. So it wouldn't matter where this rod is located. Gravity is always going to be straight down. So the first part of our diagram, we have F sub g. Let's do it. Let's just do a little circle here. We'll represent our mass as a dot. Common physics thing to do. So F sub g goes down. This is F sub g. Now we have another force here, our F sub b. And we know the length. We're given the length of the wire here. Is L. And we're given the current I flowing through this. So we can find our force from the magnetic field, which is perpendicular, so we don't have to worry about our sign of the angle here. F sub b is equal to ILB. So the current times the length through which the current flows times the magnetic field. And we have all of those, so we can calculate that. Plug in all those values and you'll get your F sub b. So now we have these two forces. we need to find out what direction this F sub B is in so we can relate it to F sub G. So now we're going to need to use the right-hand rule. So we have our current direction and we have our magnetic field. So that makes it easy. Point your hand down, fingertips towards down in the downward direction, and then your thumb pointing in the direction the current is flowing. So your fingers will point down, your thumb will point, in this case, your thumb will point straight out of the page or straight towards your chest. So you have your fingers pointing down and your thumb flowing, going in the same direction as the current, which is straight towards yourself. So that will leave your palm pointing straight to the right. So in our diagram here, we can add our force from the magnetic field straight to the right. I'll do that one more time for the right-hand rule, because I know that can be a little confusing. You do your fingers point in the direction of the magnetic field, which in this case is down. And then you point your thumb in the direction the current is flowing, which this is three-dimensional. So in this case, the current is flowing out of the page or from back to front towards yourself. So your thumb is pointing straight towards you. And then your palm, your open palm, points in the direction of the force, which in this case, your right hand is pointing down with your thumb towards yourself. Your palm is pointing straight to the right. So that's what causes this to swing up, because once the current is applied here, the magnetic force pulls it straight that way. The only thing that stops it are these two blue strings attached to it, which is what we'll want to find the tension in. So now we have the direction for both of our forces. We have force of gravity, which always points down, and we have our magnetic force, which is pointing straight to the right. These two are perpendicular to each other. So how do we relate them? Well, if we treat these as two vectors, we can move this F sub B to the tip here and add it. So it's the same magnitude, but just on the tip. So we've added these two vectors. And now, geographically, the sum of those is from the center to the end of the added point. So this is the sum of the two vectors, the bisector of them. And this is the same angle that we want here, because FG points straight down, so does this vertical line, and that's where this angle is measured from. This angle here is the sum of the two vectors that are applied to this rod, which is this sum here. And we have a neat little equation that relates all of these things. The famous Pythagorean theorem, which states that, if you don't remember, it's a very famous equation. C squared is equal to a squared plus b squared. This is something you will probably see again, so it's good to understand what this means. So this equation applies to a right triangle, which is what we have here. So this equation says that the square of the legs, which are A and B here, is equal to the square of the hypotenuse, which is this side. And we want to find out what this side is. We have A and B, those are our two forces that we calculated before. So if we square them and add them here, so we have the force of gravity, which is the A side because that points down, F sub G, plus F sub B, which is our force from the magnetic field pointing to the right, that gives us our net force, which I will just call F sub n. Or you can call it net, so you don't confuse it with normal force. This is our net force, total force, the sum of the two forces. And this is squared. These are all squared terms. So now to find this F sub net, because this is the total force, this is the force we want, you need to take the square root of the whole thing, which gives you f sub n is equal to the square root of f sub g squared plus f sub b squared. And we found both f sub g and f sub b. So this is simply just plugging in those answers that we found earlier, squaring them, adding them, and then taking the square root. And that gives you this net force here. So we have the net force. We want to find the angle. We want this angle here. So now, along with Pythagoras' theorem, we're going to have to apply some trigonometry. So we have a and b, or you could do arc sine or arc cosine because we now know c as well, which in this case c is this net force. But let's just stick with the two values we've been using this whole time. So we can use arctan, or the inverse tangent. Tan to the minus 1. Now this gives you an angle. What is it of? So tangent is the opposite over adjacent, or sine over cosine. So it's the same thing here. Our b, in this case, was our f sub b. So we have our magnetic force, f sub b, divided by our gravitational force, f sub g, or the a side. And these are two numbers that we already have. So simply divide fb by fg and then take the arctangent, or the inverse tangent of it. And then this gives you phi, our angle that we wanted. All right, part A solved. We now have the angle. What is the tension on both of these two strings now? We have our net force, but this is split up between two separate tension points here. So all we have to do, this net force here is at the center of gravity. So it's as if it's from the center point here pulling, and you have two strings on each side. So to get your tension on both strings, or each string individually, you simply divide your net force by 2. So the tension in each string, so each string will experience a tension of your net force divided by 2. Each string. And there you go.